Hi, my previous video on this Ling electrodynamic shaker was very popular, so I thought I'd do a follow-up video to this. So I'll link it up here if you haven't seen it, and down below. Highly recommend you watch it. It explains what electrodynamic shakers are, shows you inside this thing, and we have a play around with it. It's for testing. It's designed to shake PCBs, just like this. You shake them in this direction and change your rotation, this direction, and not just shake like this, but actually over a whole frequency span. So this one goes from a couple of hertz. I've got this at 5 hertz at the moment. You can count those if you really want to, and it can go up to, like, many kilohertz. They usually top out at around 10 kilohertz. So these electrodynamic shakers are great for testing PCBs and products and assemblies, and you're basically testing them to see if they can survive transport, or they might whack a satellite on here, and like a really big one, because you can get ones the size of cars and trucks, and you can shake a whole satellite on there to simulate, launch, or, your space probe to simulate re-entry. Or now, I'm going to show you how to set up one of these, and it's all about a mathematical term called coherence. Now, hopefully I'm not going to lose a lot of people, but it involves using, once again, my very cool HP, none of this Agilent or even Keysight rubbish, HP 35660A Dynamic Signal Analyzer, or DSA. And this is the bread and butter tool for the industry I used to work in, the seismic industry, where everything was like low frequency stuff. I mean, this thing only goes up to 100 kilohertz, 50 kilohertz if you turn on 2 channels, right? So these things are designed for really low frequency stuff, but they go right down to DC, they're low noise, and they're purpose designed. And as you'll see, they have the mathematical capabilities to actually measure coherence, which is a fundamental concept of setting up one of these. So you can buy your $10,000 calibrated electrodynamic shaker, you can buy your $1,000 accelerometer here, and then you can pay another $1,000 to get it NIST traceable calibrated. Here's the little accelerometer here, and you might think, well, I've got all this calibrated gear, this is fantastic, I can just whack my accelerometer on here, I can have another one on my product PCB that I'm shaking, and Bob's your uncle, I can just get these beautifully calibrated measurements. Wah. Couldn't be further from the truth. If you don't set up your jig properly, and you have to do this before you take any serious measurement at all, then your measurements are absolutely useless. In the industry, if you hand in a test result report and it doesn't have the coherence data that I'm going to show you setting up today, then they're just going to toss your report in the bin, because it's absolutely, all your data is absolutely worthless if you haven't proven that your shaker table, in this particular case, and your setup for the particular measurement that you're taking at the time is set up correctly. So that's what this video is about. I'm going to show you how to set this up and the importance of coherence. Now, of course, I have to mention that you don't need to do any of this that I'm talking about in this video if your goal is just to put your product on a shaker and then just shake the crap out of it until something fails. If that's your goal and you're not doing any quantitative measurements at all, using little accelerometers or bigger accelerometers like this one, then that's fine. You don't have to worry about any of this. But if you're doing any quantitative measurements, you have to do what I'm doing as a first step. Absolutely essential. Now, you can think of a dynamic signal analyzer is just like a spectrum analyzer, or like an FFT analyzer. In fact, that's what they're often called, FFT analyzers. But this one is specifically designed, as I said, for low frequency measurement. Goes right down to DC. That's where they come into their own in like physical measurements like this, or your physical phenomenon that you're typically dealing with in vibration and sound and other physical type things. They're all down in the DC to tens of kilohertz range. So this is the bit of kit that you want, and it's got the mathematical functions, as we'll see. So it works just like a spectrum analyzer. You have frequency on the x-axis. I'm actually starting from 0 hertz here, and I'm going to 200 hertz, and that's what we're going to analyze today. And on the y-axis, we've got dB volts RMS here, and I'm actually feeding in a 100 hertz sine wave, and there it is. You can just get the peak at 100 hertz, and if we feed in a sweep, you know, we'll see a flat frequency response here because I've just got the source actually connected directly to the input channel 1 here, and that's what we're seeing. Simple. But the real advantage with a dynamic signal analyzer is all the mathematical stuff that you can actually do, and you can do it when you include a second channel like this. So you'll notice that we have the options of just getting the frequency spectrum of channel 1 or channel 2, PSD, I've shown that in another video, that's the power spectral density, and you can get time as well, so it can just work like an oscilloscope. But then you can get, well, you can get frequency response, but then you can get what's called coherence down here, and that's what this video is all about because it's so important. It's related to cross spectrum as well, and you'll notice that they're all grayed out because we don't have the second channel enabled. So if we actually go into our 2-channel measurement here, then we'll find that we'll actually get all of these and we can enable these. So what we need to do is enable what's called coherence measurement here. Okay, before I freak you out with what coherence is, let me explain what we're actually trying to measure here. Now, we have a signal source here, so it can generate a sine wave, it can generate a sine sweep, which is called a periodic chirp, or as we're going to use here, it's going to generate a random frequency over the frequency range of interest, 0 to 200 hertz. So we've got our signal source. This is the input to our system. This is our system here. Our shaker table is a system. We have an input, which is our signal that we're feeding in via our big power amplifier over here. But that's the input signal to this electrodynamic shaker here. And then I'm feeding that input signal into channel 1 of our dynamic signal analyzer so that we can measure the input. And you guessed it, channel 2 is going to measure our output here. So our output here, this comes from our accelerometer. Now, it can be this tiny little PCB Piezotronics shear accelerometer. This is designed for really small systems. It's absolutely tiny, one of the smallest ones you get. This is actually designed to be glued onto here. This is an adhesive mount. So we're going to put the accelerometer onto our shaker plate here. Or we could use a bigger one in this particular case. This one's got a big ass magnet and it just, boom, attaches to the plate like that, or you can screw them on. They're the 3 different types available. Geez, that's powerful. So the system we're trying to measure is the input to the shaker here and the output from the accelerometer. So what we're going to try and measure with coherence here today is we're going to try and ensure that this setup that we've got, this crude, pathetic setup here, is ready for measurement in that it's linear, it doesn't have any issues, it's got no noise associated with it, it's got no other vibrational modes or anything like that. There's nothing in this system that is going to cause a problem. Then once we set it up, our accelerometer will actually go onto our product, onto our PCB under test. For example, we want to get a quantitative measurement with the accelerometer in, say, the middle of the product, how much this board is flexing, for example, over the vibrational frequency range. So that will be our output. But the values we get here won't be worth anything unless we know that our system itself is set up and it's coherent. So what does coherence mean? Well, it's actually a mathematical concept, and if I put up the formula, I'm probably going to freak you out, but it doesn't matter. Don't worry about the formula whatsoever. Coherence is a mathematical concept, and the coherence has to do with complex mathematics, which has, of course, real and imaginary parts. That's why DSAs have real and imaginary measurement components, and the coherence is used in all sorts of other measurements internally in the scope as well. Basically, if we've got an input to a system here and we've got an output to a system, how much does this output signal that we're getting correlate to the input signal? Like if we're putting in a perfect sine wave into this thing, are we getting a perfect sine wave out? Basically, and it does that for every frequency element over the entire frequency range. So basically, think of it, how much of the output is correlated to the input, and you want, obviously, 100% correlation, because if your output signal is not 100% correlated with your input signal, the shake that you're putting into this thing, then obviously you've got some sort of non-linearity in your system. You've got noise in the system. You've got vibrational modes in your daggy stupid plate that I've got set up here. And we'll hopefully be able to see the difference in a minute with that. And you want to make sure that your system is set up, because once you go to do your quantitative measurements, if you haven't done your coherence measurement and ensured that your system is completely linear and set up, then all bets are off, your data's useless. So here's actually a coherence plot here, and this is once again over frequency 0 to 200 Hertz, and what the coherence mathematical function gives you is a value between 0 and 1 here. This is not like 1 volt or anything like that, right? This is a factor between 0 and 1. And if your factor is 1 up here, then you have perfect correlation. If you've got 1.00000 pops out for your coherence up here, that means at that particular frequency, we can move the cursor in the middle there, at 100 Hertz, we have a coherence of 0.99. And that's excellent. Basically, you know, anything above, like, it depends on what type of measurements that you're trying to take, but you know, in a system like this, above 0.95 would be like considered like pretty schmick. So this is ideally what we want, is a coherence value that's completely flat over the entire frequency range. But of course you can see, like at 10 Hertz here, it's starting to roll off, and we're not worried about that. That's just a limitation of our system here. So things in this particular system that might cause your coherence not to be a perfect 1 like you want it at a particular frequency. You could be getting noise in your measurement, you know, you could be getting like electrical noise pickup, you could be getting triboelectric noise on your cables, which is basically the vibration couples through to the cables, and then your output signal that you're getting from your accelerometer is then no longer correlated with the input signal. So it's basically uncorrelated noise is one of the factors that'll cause your coherence to drop. Now, if you've got a really crappy shaker, this one's a particularly good one, but it might be non-linear. And that non-linearity could be in the coil itself. It could be the fact that you're overdriving it. It could be that, you know, you've got like a real dodgy plate sitting on it that's just hanging out, flapping out in the breeze over here. And if you've got your accelerometer over here, then you might have a vibrational mode on this plate, which causes non-linearity, for example, and that will screw up your measurements. Or you could have something that's loose on your plate and it's shaking around and things like that. That will cause uncorrelated noise that's not coming from your source. It's inherent in the system, and that'll cause you to drop in coherence. Another thing that'll drop the coherence is any delay in the system. If you've got any phase delay, measurement delay, or anything like that, that will cause a drop in coherence as well. So let's actually assume that this is our vibration test jig that we've assembled, and we want to do quantitative measurements on it. So let's set this up and test how linear this system is, see what the coherence performance is like before we take any measurements whatsoever. Because as I said, absolutely essential to do this before taking any measurements. So what we're going to use is we're going to use our little ICP accelerometer here, and I'm going to just attach this to the plate. I'm going to be really dodgy. Okay, normally you glue these things with super glue, but I couldn't be bothered. And I think it's going to work fairly well with a bit of electrical tape. She'll be right. And I've got it right near the actual armature over here like this. Now these accelerometers are touchy little beasties. They actually require a constant current source. In this particular one, it's a couple of milliamps up to 10 milliamps, so I'm going to put it around 5 milliamps. So I've got my constant current source here set up for 5 milliamps, and it requires a compliance voltage that is anywhere from 18 volts up to 30 volts. If I disconnect the accelerometer, ta-da, there we go. I've got it set up for a 20 volt compliance voltage, and then when we plug in the accelerometer, we're getting this is smack in the middle of its nominal range, so 9 volts. So this gives it the DC bias point. So we have our 5 milliamps coming in here, and this is powering our accelerometer. Now I'm tapping off that with an AC coupling cap here, a 0.5 microfarads AC coupling cap, which goes into our input, because the inputs are not that robust, and you can actually blow them up. So you don't want to be using like high voltage, high compliance voltage sources, even though this does have an AC coupling input option, and we're going to be using that, yeah, I just want to be belt and braces to ensure that no DC is going to the input here. Okay, I've set it up for 0 to 200 hertz span here. Now, you can actually do a periodic chirp, like, whoa, it's sweeping through the frequency range. It's called a chirp, but it's basically, you might know it as a frequency sweep. And that's useful for some things, but we generally don't use that for this sort of test. So we're going to choose, actually, a random noise. And you might be able to hear that now. And that's inputting random noise over that frequency range from 0 to 200 hertz. So then when we average our data, we take multiple samples, we average, you know that you're going to get energy input at each frequency over here, because it's random, and eventually you'll build up a waveform over frequency. Okay, so we've got our coherence measurement here. Our input, we can like auto range our inputs so that it gets a suitable, selects a suitable input range. And I've turned on averages as well. Let's just get an RMS average, and then we'll just start like this. So it's going to now, it'll take a few seconds before it starts getting a couple of averages, and then it starts displaying it. Bingo! We now have, this is our coherence response over frequency, and you'll see it slowly gets better as we take more samples, and then it gets more samples at each particular frequency. And you can see that this is actually a pretty schmick response. The coherence is pretty darn close to 1 over the entire frequency range, and this is just for a bit of tape like this. And if we actually glued it down, we might get this smidge better, but yeah, that's not bad performance at all. So what happens if we move our accelerometer right out to the edge here? Let's actually do that again. We've got to restart. Before we had it right on the armature here. Now it's out here flapping around in the breeze over here. And, oh, that's not very good, is it? Look at that. Really have something happening here at 100 hertz, and it's all over the place. It's not just 100 hertz, but what's happening here is our system has become non-linear because we've moved the accelerometer from right on the armature here, right out here. So we now got it. So now this is taking into account the mechanical properties of this plate. And with this plate flapping around in the breeze over here, going wiggle, 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 yeah, right? It's causing all of this uncorrelated noise that's not coming from our signal source. It's coming from the mechanical. It might be the mechanical resonance. It might, just basically the non-linearity in the system. Bam! Look at that. So this is horrible. So if we built this and we were wanting to do some quantifying measurements, and our accelerometer's mounted over here like this, then if we didn't do this coherence measurement, we would have had no idea that this thing is horribly unlinear between 80 hertz and 140 or something. Okay, so let's run the same test again, but we'll use this accelerometer. This is a Vibrametrics Inc. made in the United States of America, model 7000. It's really old, but it still works. It's got a magnetic mount, so let's, put it on there. But this one is much heavier. I mean, this weighs practically nothing, but this one is heavy as it's designed for much bigger systems. So that extra weight's going to affect the magnitude here. It's going to possibly affect the mechanical mode of this plate hanging out in the breeze here. And let's start that again and see how this one performs. That's not too shabby at all. And it's going to get better and better as we build up more data there with the averages. But yep, that's a really schmick response, is it not? Now what happens if we move this all the way out to the end here? So that wasn't there before, was it? So if we slide that back, Yeah, you can see, yeah, it is very different. So that was causing, down at about 10 hertz there or something, yeah, that was causing an issue, definitely, just by having it out there like that. And this is smart enough to know that if I try and measure coherence without turning averaging on, yeah, nah, you can't do that. And as I mentioned before, the coherence is actually related to the cross spectrum, and they're mathematically, they are actually different, but we can actually do a cross spectrum measurement as well, and you'll notice that it's fairly linear, but we won't go into cross spectral analysis versus coherence, but suffice it to say, they are intimately related. Pop quiz, hot shot. We've got our nice response like this. It's all happening, exactly what we've seen before. Now, I'm going to change something, see if you can spot the difference. Check this out. There's something horrible happening at like, what, 65 hertz there? Something like that, right? Pretty awful. You might think, oh, there's something wrong with my thing. Or if you've actually got your second accelerometer on your product, on your actual PCB, and you're getting your response, and this is what all this coherence is about. If you're getting this response, you might think that your product is doing that, but it's not. It's not your product, it's not the jig. What has changed? Well, it's the auto range. Your input values matter because we're actually clipping. You might have seen there that we'll get in an overload on channel 2 here, which was the accelerometer input. Now, if we put it back to auto range to range it properly, bingo, we go back to exactly where we were before. And this is the importance of coherence. There's all sorts of factors that can go into this. It's not just the physical jig itself, the physical mounting and everything else. You have to ensure that your entire system is set up correctly, because at the moment we're just testing the response of this plate, and you would leave a reference accelerometer on the plate, but this is just setting the system up. Then you'd add a second accelerometer onto your actual product, or multiple accelerometers onto your product, and you'll get your various frequency sweeps to see if they meet some military performance vibration standard, or whatever it is, your in-house company standards. Doesn't matter what it is, you'll get a response on here, and you might see all these dips and everything else, and you might think, oh, I've got some mechanical resonance in my product, oh, I better redesign it, quick, panic. And no, you just haven't set up your jig properly. And that's the importance of coherence here. This is why I was saying, if you don't have your coherence data with your report of your test results of your product, then it's worthless, because it shows that you have not put any thought into setting up your vibrational test system. And your data that you get out of your accelerometer, your product, is absolutely worthless. Doesn't matter how calibrated your accelerometers and charge amplifiers and your shaker, electrodynamic shaker is. It doesn't matter a rat's. So until now, we've been playing around with that random generator, but we can't actually do a sweep. So what I've got is an external function generator here. I'm actually going to set it up for a 30-second sweep here from 10 hertz to 200 hertz, which is our frequency range of interest. There we go. It starts out slow, and over 30 seconds, it will sweep. So let me start our acquisition. Let's have a look. And because we're only at one frequency, you'll find that it's going to slowly sweep across like this, and eventually 30 seconds later it will have swept all the way across, and we will actually get coherence values. Now this is showing a real interesting result. Now here we go, it's getting 150, it's almost at 200 hertz here, and boom, and then it can of course keep doing its RMS averaging and whatnot. But look at all these notches that we got here. What's going on? Once again, this is a gross example of where you might get a response that you might think's coming from your product, but it's not. It's because you haven't set up your sampling system correctly. So can you guess what the problem is here? I'm going to change something here on our signal gen, and we'll do it again. It's similar, but more frequent. Okay, I changed it yet again, and look at this, our coherence. I actually started it a bit late there. And look, we're getting this little wiggle, 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 yeah, in that signal. Check it out. Look at that. That's interesting, isn't it? What's going on here? Is this some sort of little micro resonant thing happening in here? What's going on? Well, for those who were paying attention that it took a bit longer, you would have realized that I was changing the sweep time. It started out as 30 seconds, then I increased it to 60. And you would have seen that those dropouts we got here were doubling in frequency when I changed from 30 to 60 seconds. So it's a function of our record length and sample time in our DSA compared to our sweep speed that we're actually doing this at. Yeah, this makes a huge difference in the measurement. And if you just whack your accelerometers on your product and started getting your sweep and thinking that you're getting the correct values because you've got your whiz-bang expensive calibrated accelerometers and software and everything, no, if you haven't set up the system correctly, you can get all sorts of wibbly wobbly stuff that has absolutely no correlation to the product that you're actually testing. I was getting sick of the tape here, so I've actually super glued it on now. I should have done that from the start. Now check this out. I'm actually setting a sweep time now that is uncorrelated with the anything to do with the sample rate. So 7.7 seconds sweep time, just a random number. If I start a new sample, so this is 7.7 seconds sweep time, and you'll notice that, right, it's all over the shop, but eventually this will get better and better as we do more averages, and because it's uncorrelated time-wise, then slowly we're going to build up a complete picture. So you can see it there. Yeah, it's slowly building up a complete picture of this thing. Now, I'm not saying this is the correct method to do it. I'm just like showing this as an example of how you can have like a sampling and other time correlation errors, which will cause a drop in your coherence. There we go. We've almost got the basically the full response of this thing now. So time and sampling correlation is yet, and phase correlation as well, as I mentioned, can be another source of error that you can get in your measured signal, that if you don't do this coherence measurement test, you'll never be able to see it. The coherence test is a definitive way to show that you've got no errors in your system, or as few errors as possible in your system before you actually start your proper quantitative measurement. Here's another example of error that we're getting in. You can see that the response is not that great here, is it? It's like it's glued on. This response is supposed to be really nice. Can you spot the error? Maybe you can hear the error. It's these damn screws rattling around because I haven't tightened them up. Tighten them back up, start that again, and you'll see that our response is much nicer. We didn't get all this random noise and crap in there, which then would have gone through onto our output signal. All of that crap was happening because we had loosey-goosey stuff on our setup here. And when you're setting up your system like this and getting your coherence measurements, it can matter that whether or not you've got your actual product that you want to test on your shaker table, because it has extra mass. It can change the dynamic properties of the shaker, which can introduce non-linearity into your system. And look, I haven't changed anything else. All I've done is screw on that PCB there, and we've got this huge notch here at 32 hertz or something like that. Like, it's terrible. And then when you go to put your accelerometer on your product here, you're going to get all these weird and wonderful results that you didn't expect. And you might think that you have like a design modal mechanical problem in your product that you're actually testing, when you don't. It's your setup. Sure, this is like an extreme example with it flapping around in the breeze, but hopefully that gives you a good example of what can happen here. So there you go. I hope you found that interesting, the importance of coherence measurement. So when next time when somebody shows you their test results for their vibration tests that they've done for their product, oh, look at this. Ask them, hey, where's your coherence data? Because it ain't worth jack unless you've set up your system properly. So there you go. I hope you found that really interesting. Coherence. This is not something that you'll learn in school. Basically, you will only learn this hands-on. I guarantee you will learn about coherence the very first day you start trying to do vibration testing on everything, and your results go to crap, and you're wondering what the hell happens. Then you discover the world of coherence and setting up your jigs and characterizing your test jigs properly so that you know the results are going to be good. And anytime you change anything, in fact, anytime you do a measurement, you should do a coherence test first to make sure, sanity check, your results are what you expect. Because there's so many errors that can go into introducing non-linearity into your test system. Once you get non-linearity, your measurement output data, you don't know whether or not it's real or imaginary. Get it? Real and imaginary complex. I'm here all week. Anyway, hope you found that interesting, invaluable. If you did, please give it a big thumbs up. And as always, you can discuss down below. And as always, EEV blog forum, all that sort of stuff, and all the different channels I'm on. I'm on every platform. Catch you next time.